that we had to do was make a bottle rocket, and this is ours right here. And then, right, so the materials, so the materials were these. So an empty bottle, soda, and cardboard fins right here, and then a cardboard top, the cone, and colored tape to like design it and everything, and scissors and the usual stuff. And for the fuel, well, water. We needed water for, well, half of the fuel.
So all the materials were gathered and we designed a model, and then from the model we executed what we were supposed to do. So we had Yash doing the fins, Neil doing the tip, Katrina was taping it, taping, and then we just like put everything together, and that was our final result.
Alright, so the physics behind, so how did it go up in the air? So basically, so the Newton's third law, every reaction has an opposite and equal reaction. So when the air, so there was so it was water, 1/3 water be filled up with the bottle, 1/3 water. So in order to get, so if we just left it without pumping any air in it, nothing would happen. The water would come out normally. So we have to pressurize it. So we had to pump the bottle with air, because air, well, gas is compressible but not liquid. So gas was compressed, and it was all this air inside here, and the water was just waiting to just get out. It just wanted a way of find a way to get out. So when the rubber stopper was pulled, the water rushed out because it needed a place to go. It couldn't just stay here, or the bottle would just explode. So it got out, and it was coming out with a faster velocity, which hit the ground, which created the rocket to go up and propel it up in the air. And that's it went like 30 feet in the air, basically, 30 meters, feet. And then this is the video we recorded. It's on YouTube, guys, if you want to watch it.
I know.
Oh, yeah.
You put your Yahoo account in Google.
It's not supposed to know.
It worked.
No. This is before YouTube was bought. So
Oh,
yeah.
yeah.
Oh yeah, I forgot this. Here, where's the link?
Alright, so as you can see,
So the professor was pumping the air with the pump right there.
and the bottle was right here,
So
held by two sticks, so it wouldn't.
So
Tip
yeah, so it
over.
wouldn't go at an angle and hit somebody in the eye.
Yeah.
So just leave it. Just leave it.
Look at all the people gathering. Oh my god.
I was scared.
Alright. Oh yeah. That was it.
So yeah. So that was pretty much.
Am I in the
And so after we had to record the degree and it went, so the feet up meters, I mean, it was 30 meters, it went 30 meters up in the air, and
2
80 degree
after
angle.
1?
And that was our activity, our presentation. Do you guys have any questions or?
Oh yeah.
Foil.
I guess not.
Weird now.
David.
Yeah, I'm not sure.
Frank.
We did, what was happening? Oh, we were in current trends in physics 1, and we did activity. Oh, we did the gravitational, it was a staircase activity where we went up the stairs to see how fast we went up and how the potential energy, how much potential energy we had when we went up. And we did the motion sensor where we moved back and up in front just to follow the graph. Where it went up and down, so we had to follow, like trace the graph just as we moved, so we would have a perfect, we would match the graph as we were moving.
Alright.
Okay.
Once you see this picture, you're probably thinking, oh my god, this physics this doesn't look like a lot of fun anyway. But I'll tell you right now, there's no better way to get things moving than the motion sensor. And this lab that we did involved this graph right here, and there were 4 different graphs, and what we pretty much had to do was stand in front of a sensor, the motion sensor, and depending on the distance that we were from the sensor itself, the graph, it started off like right here. You see the red line? That's us moving. And we had to match the line right here in gray. And as you can see right here, we were pretty close at 95.5%. Pretty much what? Yeah, that was David's score. Go David!
David's like the best apple.
Yeah, it was this guy.
Oh, really?
No, Frank's one.
He's got the moves, you know?
And I was the worst one.
I know.
What pretty much happened here is that once you go in front and you approach the sensor, the red line you see right here is going to go down. And once you go back and you're farther away from the sensor, the slope, it's going to increase. The slope also depends on your speed, as in how fast you're traveling and going back and forth. And depending on that, the slope's either going to rise in a very steep way or in a less of a steep. This right here is the equation for velocity, which is delta x over t. Now, don't get confused by this triangle right here. This is just delta. And delta x means displacement, which is the change in distance. Right? Now, as you can see, this is a picture of me. Legit.
Good likeness.
No makeup, no filter, no Photoshop. That's it right there. That was a little animation to show you exactly what happened that day. That was me doing that. And when you saw it, when he went back, the slope of the line went up, and when he was at rest at this point, the slope of the line was 0, as in the speed was constant and the distance didn't change. So as you can see here, the y-axis is the displacement and the x-axis is the time. Now displacement, as I explained before, is the change in distance. And the reason I didn't put distance here is because if that was distance, instead of going back down to 0, it would have went up. Now, what I did was I tried to be very bold, and this is real footage from what happened earlier. And if you go on, don't try to trick the motion sensor, because I died. And then I came back.
That's no good.
Okay, we did an experiment with projectile motion, and well, as you can see, the point of this little game was to get to this target using different angles, different initial speeds, mass, and diameters. And we did this without air resistance to see what it was like, and then we also did it with air resistance. So, like so far the angle's at 80, so should we change that? Yeah, if you pull on the cannon, you can change the height too.
Aww.
Yeah, you can
Put it
change
lower.
different things.
Put the sound on.
45 degrees.
45 degrees is like
Oh.
the degree where it shoots the projectile the farthest. As you can see, 45 degrees, it went way off screen.
Oh, we didn't get the target. Is that Jackie?
So, one of the experiments that we did was called the essential experiment. We used principles of projectile motion and some physics equation to calculate the initial velocity. So what we did is we took some water balloons and we shoot them across the field. We shoot them in two directions, horizontally and also vertically. We did two separate trials. First, two people were holding it and another person was shooting. We measured for horizontally the height from the projectile, and then we measure how far it went. Then using some physics equations, we were able to calculate the initial velocity with which we had pulled the water balloon. Then we also did another one vertically. Two people were still holding it, and we showed it directly out to the sky. And this time, however, we only measured the time that the projectile was in the air, and we used some other equations to calculate the initial velocity. We have a small video that shows our experiment.
Yay.